Okay, so on the agenda for today, first we're going to have Paul Sear from Kleinschmidt be talking about how beyond design basis operations affect dam safety. Then Dan Gessler from Alden will be talking about predicting spillway performance for beyond design basis events. And then we'll have from Todd Barber at Southern Company the owner's perspective on spillway safety with beyond design basis operations. So as an introduction, reviews of spillway safety can trigger updated capacity analysis of the spillways. And what can happen is once that's done, the spillway may no longer meet the flow criteria. And we will be talking about some tools that are available for determining whether changes are needed and what those changes may need to be. But those tools have limitations, and we'll be talking about those as well. So to start out, we have Paul Sear, who's a PE. He's a principal of Kleinschmidt Associates. He's been with them since 1977. He specializes in dam safety and vulnerability security inspections, design and stability analyses of dams, floodgate design, and construction and maintenance inspections. Since 1988, he's been recognized by FERC as an approved independent consultant and a PFMA facilitator. He served on the FERC's Gate Committee, developing guidelines for their proposed risk-informed decision-making program, and he was the secretary and contributing author of the publication Civil Works for Hydroelectric Facilities, Guidelines for Life Extension and Upgrade. And that was written by a hydropower task committee for the ASCE Energy Division. He has a bachelor's in structural engineering from Northeastern. Paul, the floor is yours.
Yes, thank you very much. I assume you can hear me fine.
Perfectly, Paul.
To start with, as David said, I'm an independent consultant. My job, probably to the chagrin of most licensees, is to look at the dam and pass judgment as to whether it meets various agencies' criteria. So when I show up on the site, I'm not only interested in the physical condition of the structure, but I have to look at its hydraulic capacities and its stability analyses. So as time marches on over the last 100 years, we've come to see there is a need for higher spillway capacities. The original assumptions made in the design of a project do not meet the current design requirements for either spillway design flood, an inflow design flood, or the probable maximum flood. Once you decide you need more capacity to meet the governing agency's design requirements, it all usually equates to one thing. We have a higher impoundment level. So the increase in an impoundment level starts to chase us. It has a direct negative impact on the stability of all the water retaining structures, not just the spillway. And it's the result of increased hydrostatic load on the dam, along with increased uplift pressures. David, I don't know, we are missing figures on these slides.
Oh, just click through and they'll come through. So
sorry. Okay. Sorry, folks. So here is a real example of a project that was built 1915. It had a design head of 15 feet at the time it was constructed. Today, the IDF is equal to the PMF, and it's 30 feet above the crest. So we're looking at a current design requirements that's twice what it was designed for. So the new slides that just showed up is a typical OG crest showing the design head. So that'd be the top right-hand section. And then what happens on the lower two bottom ones is as you jack up your design head, there's impacts on the spillway crest, on the tailwater. We have the chance for cavitation down the slopes. But the Army Corps of Engineers has indicated that if your if your demand on your crest is about 1.3 times what the original design head was, you're going to result in negative crest pressures. Well, the negative crest pressures is a negative impact on the stability of the structure because it's an extra force that, frankly, was never accounted for back in the, I'll just say, before 1940. We also have changes that have occurred on a spillway crest over time. Spillway gates are replaced. Obermeyer gates are an excellent example of a lot of people changing out old crest gates or flashboards. There's also things, and I think many of us in the north can appreciate this one, we do a lot of resurfacing of a downstream face of a dam. So ask yourselves, how many times have you actually restored that OG crest to the original geometry that it was based upon? All of these have one common impact. It results in change of the impoundment level. It results in a change in crest pressures, and they're all due to the spillway discharge capacity being increased. The figures you show are of a real project. The upper right-hand side, it shows of horizontally rotated flashboards. They're 5 foot high. They were originally built as just vertical flashboard pins. And at some point in time, it got changed to a horizontal. The photograph down below it shows what it looks like after it's been rotated, but before it's been restored. It's supposed to be self-righting, but as you can imagine, you get debris underneath them. They don't right themselves too well. So even though you have additional head on this structure, ask yourself, what does this new flashboard arrangement do for my crest pressures? Increased discharge capacity also results in a direct impact to the tailwater. As you increase your flows, you could literally blow the tailwater away. In other words, you'll suppress it right at the base of the spillway, and in suppressing it, you're reducing the resisting tailwater forces that may occur against the spillway. At the same time, the increased velocities may actually result in a favorable positive pressure along the toe due to the change in the direction of the velocities flow. So tailwater depths and the pressures on the downstream side of the structure have a direct impact on the stability of the spillway dam. They may not affect your non-overflow structures, but they will affect your spillway dam. Earlier I said you could have an increase in positive pressures at the toe of the dam. If you happen to have a dam that has foundation drainage systems on it, the velocities increase the pressures on the outlet of the foundation drainage system. So the question that always gets asked is, do those higher pressures at the outlet get translated back underneath the dam via the drainage system itself? And do those pressures result in increase in stability of the dam? So everything we were talking about, that I talked about before, has to do with what was happening on the head pond end. Dams that are affected by, dams that are regulated by state agencies are governed, the downstream development will have an impact on the dam's discharge capacity. As development increases, the dam's hazard classification increases, and usually with all the dams, the higher the hazard classification, the greater you need in discharge capacity. So, which means you get a choice. You expand your spillway, or you discharge more water over the spillway that you currently have. So this actually closes my part of the discussion. Again, I'm viewing the structures as they exist, and I'm passing judgment back to the owner to saying whether they meet the state or federal agency's current design criteria for spillway capacity and stability analysis.
Thanks a lot, Paul. Appreciate it. Next up is Dan Gessler, who's going to talk about predicting performance of spillways for beyond design basis events. Dan is a principal of Alden. He has over 25 years of experience in numeric modeling. Since joining Alden in 2002, he served as a senior hydraulic modeler, a project manager, and a principal in charge using computational fluid dynamics and physical models to investigate a broad range of hydraulics and river mechanics problems, including complex sedimentation studies and spillway studies. Before joining Alden, he worked as a research scientist and assistant professor at Colorado State University, working on three-dimensional hydrodynamic sediment transport modeling for the Corps of Engineers. He has a BS, MS, and PhD in civil engineering and hydraulics from Colorado State University. Dan?
Thanks, Dave. I appreciate the introduction. My presentation is going to follow on to what Paul talked about, and I'm going to look specifically at predicting hydraulic performance of spillways for beyond design basis events. I'm really focused mostly on the hydraulic side of things here. So the place to start perhaps is in defining in my world at least what constitutes beyond design basis, and at least for the purpose of today's discussion. So the most obvious one is a greater flow, and that can happen for a multitude of reasons. Perhaps a revised PMF can result in a greater discharge or required discharge capacity of a spillway. The second one that we could talk about is a change in tailwater level, and that can be an increase or a decrease, and somewhat counterintuitively, an increase in flow can at least very locally result in a decrease in tailwater level.
Dan, sorry to interrupt. This is Dave. I just got some feedback that some folks are having a hard time hearing you, so anyway you can move closer to your mouthpiece or speak up a bit, that would be great.
I will speak louder. Thanks for pointing that out, and remind me if you still can't hear me. So changing debris considerations as well. So this can be a partial gate blockage that might not have been considered in the original design, but where you now realize that as debris builds up on the gates, they might not all operate exactly as planned. A change in the gate type or a change in the crest shape. So if you replace one gate with a different type of gate, that may affect the rating curve for that particular structure. And then a change in reservoir operating levels. So if you are increasing your pool level because of perhaps recreational needs or other considerations, then that could change the flood routing through the reservoir as well. So you might remember Paul's picture that he showed of the hinged gate that could rotate. This is a picture, I think, of actually the same gate with debris built up, and obviously this spillway is not going to perform quite as expected because there's not a whole lot of water going through under the gate. Most of it will have to go over the top. So beyond design basis operations, what's going to change on the spillway from a hydraulic perspective? Well, the most obvious one is probably velocity. If you send more water down the spillway, then there's a pretty good chance that the velocity on the spillway is going to increase. The other one that can change is surface pressure on the spillway. And if the velocity was to change and or the pressure changes, then that could result in a change in the cavitation index for the spillway as well. So we may start to see cavitation that we weren't seeing under the design flow conditions. We can get uplift on a spillway, so even if there's no cavitation, that doesn't mean that pressures might not be low enough to generate some uplift on the spillway surface. And then tailwater level, and we mentioned this a moment ago, that a higher velocity can result in a blowout of the tailwater, so you change the back pressure on the dam. That would be one effect on stability, but it can also change the tow scour at the dam. So if you were counting on energy dissipation from that tailwater level to protect the tow, If the tailwater is blown out, that can change. And then air entrainment. And this is really limited to certain types and classes of spillways, but there are certain spillways that have to be, or that draw air as they are operating. And if we are unable to meet the air demand of those spillways, it will change how they perform. And so morning glories are a great example that entrain air, but labyrinth weirs and fuse gates, depending on the fuse gate type, will also require some air and air entrainment systems. So the next thing I want to show you is just a picture of a typical CFD model of a spillway that shows beyond design basis. On the left, you see the design flow that the spillway was designed for, and on the right you see the newly calculated PMF for the same spillway, which is significantly larger. And what you see is an increase in velocity on the bottom of the spillway chute, and you see that the trajectory of the nape has changed slightly, and it goes further downstream before it reattaches with the catch chute. So what tools do we have available for predicting performance change? Well, the obvious one is physical models. That's the one that we've been using for over 100 years now, at least as an engineering community. And with the physical models, we can measure pressure, we can measure velocity, and we can measure water level. We can capture low and high speed time-dependent fluctuations in those quantities. So if we want to know how pressure changes at a high rate of speed, we can use high-speed pressure transducers and measure those fluctuations. The biggest limitation on physical models, I guess I'll back up one step by saying, if they're properly scaled, the results of physical models are generally accepted as being correct. Now, the biggest downside or limitation to a physical model is that they can be costly and they can be time-consuming to build. So more recently, meaning within the last 15 or so years, we have been able to use numeric models to look at some things that in the past were done with physical models. And the two models that are probably the most widely used for spillways are Flow3D and OpenFoam. And with these models, we can calculate pressure, velocity, and gradients of those same quantities. But what the models struggle with to some extent is capturing high-speed unstable fluctuations. So any kind of vortex shedding that might occur in a structure is going to be hard for a CFD model to get. So let's talk a little bit more about numeric models for a few slides, and then we'll talk a little bit more about the physical models before I wrap up. So about 15 years ago, Alden compared CFD and physical model results for a spillway. And then we published those results. And we were looking at, there was the stage discharge rating curve and the trajectory of the flow. And we found the stage discharge rating curve was within about 3 or 4% of what we were seeing in the physical model. Since then, both Alden and others have gone on to use numeric models fairly extensively. We've validated a number of ours as well, but probably not all of them. Now, with each successful use of modeling, especially in the world of numeric modeling, it's probably good to keep in mind a quote from Bill Gates. And so I'll pop that up here. And that's that success is a lousy teacher. It seduces smart people into thinking that they can't lose. And the takeaway there in a numeric modeling sense is just because we can model certain types of spillways reliably, and we've shown that they work, that doesn't mean that the numeric model is going to be applicable to every kind of spillway. And so we need to try to keep that in mind and make sure that the models have been validated for the type of spillway that we're working on. So how do we decide which model is needed, whether it's a physical model or a numeric model? Well, the availability of model validation data can be a good factor in deciding what type of model that we're going to use. Model geometry is a big influence. certain geometries are notoriously difficult to capture in CFD. Very large labyrinth weirs, for example, because of the high detail of resolution that they need, can be difficult to get. Not all of them, but some of them. The size of the model domain, so very large spillways, can be a challenge in CFD. We simply run out of computer memory and computational cells to resolve the flow field in enough detail. And then the allowable uncertainty within the model results. Finally, parameters of interest can influence as well what type of model that we're going to use. So let's talk a little bit more about the limitations of CFD models. Grid resolution is usually the most significant one, that we run out of computational cells, and that'll be recognizable by when you look at the results, the flow field will break up, it'll disappear as the grid resolution becomes too coarse. Another challenge can be that these problems can be two-dimensional, and we tend to think of spillways as being very three-dimensional. But if you think of a very long spillway chute where the water depth is relatively small, that is really just a tilted two-dimensional problem. And those two-dimensional problems tend to pose a challenge for CFD. Again, we can run out of computational cells. Pressure and spillway pressures and pressure fluctuation in vortices can be difficult, so stepped spillways, and hence the picture that I'm showing on the right. We do very well predicting bulk flow parameters down stepped spillways, but if we're looking at the pressure fluctuations, for example, on the face of an individual step, those are strongly influenced by the vortices that are shed off of that step, and those are so small that we have a hard time seeing them when we're also trying to see what's going on over a large domain. And then air entrainment, and this comes down to a question of the physics involved in the model. For example, air entrainment requires a coefficient in order to get the air entrainment rate correct in the model. But where are you going to get that coefficient from? There is not a default coefficient that applies to all situations. So let's talk a little bit more about the validation of the models and how we do that. So there is little, or as far as I know, no prototype data during design basis events. So during a PMF where someone has instrumented a spillway and measured all of the performance, the velocity, the pressure on the surface, and so on. So in the truest sense of the word, one would have to argue that these CFD models are largely unvalidated, at least against prototype data. But what we have done is validate the models against physical models. And we see there, for example, that pressures on an OG spillway using physical model data, we've shown that that's fairly reliable and that we get those right. And the same with the stage discharge rating curves. So I would argue that after looking at a number of physical model and CFD model comparisons for OGs, we feel very comfortable with the results that we're able to get for that particular class of spillway. Now, we know that there are limitations with some spillways, and usually if you trace it all the way back, it comes down to a question of computer speed and that we can't get a high enough cell count to be able to resolve what it is that we're after. And then the last question when we talk about validation is an unvalidated CFD model better than no model? And in most cases, I would say yes. If the model that you're doing has been, if that class of model has been validated, then you've definitely gained insight that you otherwise would not have had. What we need to be careful of is when we use CFD models in a realm that they have never been used before, and to not be led astray by a CFD model result that is unvalidated. So that's where the caution is required. So one last thing about unvalidated models. A question worth asking yourself before you start modeling is, what if a CFD model gives you unfavorable results? And that's probably a question that is best asked before the modeling starts, so that you know how you're going to step through the modeling before you have the results and how you intend to progress. Now you can still let the results guide your thinking, obviously, but when you go in, you should try to have a plan. And I think Todd will speak more to this in his presentation as well. So tips on minimizing CFD uncertainty. Most of the uncertainty in these models probably comes out of boundary conditions, uncertainty in the boundary conditions that we have to apply. And so this is a limitation not just for CFD, but for physical models as well. It's the same issue. Next, really limiting or focus mostly on CFD or only on CFD is numeric error. So problems with the grid resolution, not being able to get it high enough. Governing equation discretization can cause uncertainty. Applicability of the submodels that are being used. So an error entrainment module, where do the coefficients in that module come from? And then before you use them, track them back to the basic research on which they are based. From that, you know how to vary those coefficients, and you can see how they influence the results of your model. So these uncertainties can be tested. And the same is true for turbulence models. You can use different turbulence models and see how they influence the results. So the takeaway is to test your models against known information. Let's talk a little bit about physical model limitations, because these are not without limitations either. Most of those are driven by scale. So large spillways can pass a significant flow. And if you were to think of a 1 to 25 scale model, which is a reasonable model scale, a spillway passing 400,000 CFS prototype is going to require 130 CFS in the model. And while that's doable, that's pushing the upper ends of what we can still push in a scale model. That's a pretty big flow to do. And then measurement limitations. Can we make the measurements that we want to make on the physical model? Can we put the pressure transducers where we need them? Can we get the velocity measurements that we want? And then finally, models that are sensitive to error entrainment have particularly unique challenges because they are required to be very large. And so we know that these models, in order to get the error entrainment quantities correct, we need to run these at a 1 to 10 to 1 to 15 scale. And that's based on fairly recent research, actually, that the models need to be that large. So if you have a case where you have a CFD model and a physical model, the question that comes up is, which results do you use? And if things go well, the stage discharge curves are going to be within 2 to 5%. What we would suggest there is that you should probably rely on the physical model. We typically see the stage discharge curve from a physical model to be slightly more conservative than that from a CFD model, and we think that has to do with the scale effects in the physical model. Physical models should overpredict the water level in the pool for a given discharge due to scale effects. So a summary then of the modeling options that we've talked about. First of all, spillway performance for beyond design basis can be evaluated. We can do that using either physical or numeric models. Second is that in addition to physical modeling, we now have CFD. And while it has limitations, it is a useful tool to help us in the analysis. When choosing a modeling approach, it's probably good to consider the project goals and the benefits of each model. So try to talk to someone that can can look at or understands both options and can give you the benefits and limitations of using a numeric model versus using a physical model. There are certainly cases where people have asked us for a numeric model and the physical model was actually only fractionally more expensive and did not have some of the limitations that the numeric model was going to have. Consider how the model is going to be validated. So there are uncertainties or errors in all of models, but think about how we're going to validate it to make sure that we know that it is useful for what we want to use it for. And then finally, anticipate how the model results are going to influence the project and try to make a plan for how to move forward through the modeling program depending on how the results turn out. So you have a strategy going into the modeling program and that you're not just reacting to the results that you get.
Thanks a lot, Dan. The next presentation will be from Todd Barber, and he'll be talking about the owner's perspective on spillway safety with beyond design basis operations. Todd is a senior engineer for Southern Company Hydro Services. He's worked for 17 years in geotechnical consulting, which included earth dam design and inspection, concrete materials testing, and forensics. His 6 years in dam safety have included emergency action plans, dam safety inspection, stability, regulatory compliance, and rehabilitation of dams, and he has a bachelor's in civil engineering from Georgia Tech. Todd?
Thanks, Dave. Yeah, I will let you know that, as Paul said, Paul has worked for us and has passed judgment on some of our dams that I'm going to talk about, and we've actually worked with Alden too, so let me go right into it. I'm going to kind of focus on our North Georgia project, which is a group of 6 dams up in northeast Georgia, starting with Burton Dam, coming down to Coochie Dam. Those are both gravity dams. Mathis Dam, I'm going to talk a good bit about in my specific examples of where we've used CFD and physical modeling. Then Tallulah Falls Dam, which a lot of people are familiar with. There's a state park in that area. It's a real nice area up there along Tallulah Gorge. That's along the Tallulah River. And then at Tugelo Dam, we have where the Chattooga and the Tallulah Rivers merge and come out of Tugelo Dam, and the Tugelo River flows down to Yonah Dam. Give you an idea, this shows you the elevation profile of these 6 projects. All these are about 100 years old, plus or minus. As you can see, they had a pretty good idea where they needed to build dams even back 100 years ago. There's about 1,200 feet of head loss as you go along this one, along, I think it's around about 18, 20 miles airline distance and a little bit more river mile distance. Back in the 80s, through some of our dam safety and regulatory inspection processes, it was determined that we needed to reevaluate our design storm, or in our case, our PMF, potential maximum flow, through our dams, and this was due to the publishing of HMRs 51 and 52 in the late 70s and early 80s. Essentially, basically, the methods for determining the PMP for these projects had changed since original design. So we did some flood studies to reevaluate the PMF for our projects. Let you know, the previous work was done using HMR 33. That was done the last time that they had looked at our PMF flows through the project was in the 40s, and then again in the 80s when we had to look at it again. Studies were done. We determined PMF flows through our project, but at the time, in the late 80s, they wanted to have a better feel of how these new PMF flows pass through our project. So they want to check things such as spillway capacity. Did we impact spillway bridges? Did the PMF elevations overtop areas of concern, things of that nature? And so in 1987, they decided to work with Georgia Tech and do a physical model of 4 of the 6 dams in our North Georgia project. 2 of the other dams had crests that were very similar. For instance, Mathis Dam and Tugelo Dam had very similar spillways, with gated spillways with piers, and so they used the information they gained on Tugelo at Mathis. And then Yonah Dam and Nakuchi Dam were both essentially free crest spillways, with one of them having flashboards, and so they were able to basically model 4 of the 6 dams. But they basically wanted to do this to check all those things I mentioned, and the physical modeling did confirm the flood studies that they had done for the new HMRs that had been published. And the new PMF elevations did indeed lead us to need to revise our stability analyses for those projects. We basically essentially got higher PMF elevations for most of those 6 dams we have in this project. Most of those dams, we did find out that with some dam strengthening, we didn't have to do any modifications to the dam. However, I'm going to talk a little bit more about Mathis Dam, and we did have to do some modifications to that dam to pass the PMF flows adequately and safely. One question I had looking back on this, like I said, this physical modeling was done in 1987. Was a possibility if they could have used a CFD model instead of doing a physical model to arrive at the same conclusions. So I mentioned I was going to talk about Mathis Dam. This is the 3rd one in the Cascade I'd pointed out. It is a slab and buttress structure. It actually started out as an Emerson Dam, but the project stopped. It was started in 1915. It was stopped, and then actually was started back under a slightly different design, so it's not exactly an Emerson design, so we basically call it a slab and buttress structure. After looking at the new PMF elevations back in the 80s, there was concern that came up whether we could pass the flows through this dam without impinging on the spillway bridge. The original PMF elevation for this dam was about 1695, which I know this is a little bit of an out-of-scale picture, but was somewhere pretty low down, just barely above the gates here, maybe about 4 or 5 feet above the gates with the gates down. Well, this spillway bridge deck is at about 1704, and the new PMF elevation was 1702. So there was some concern about when the flows hit the bridge piers upstream that it may pile the water up and create uplift forces or push the spillway bridge off of the piers, and this would lead potentially to instability of the dam. So we're trying to figure out how we're going to evaluate this, and what this led us to is looking at a CFD model. Let's model our flows now and see if we impact on our bridge. And what we found through this CFD modeling, you're now looking from upstream to downstream. It did show that condition at the piers that we're concerned about where the water may be piling up, but we found that it did not impact the spillway bridge, and so our stability was not affected by losing the spillway bridge deck over the top of the piers. But through this process, we solved one problem. We basically found out that we were not going to impact the spillway bridge, but our consultant told us, unfortunately, hey, look, you look like you're okay with the spillway bridge, but it looks like you have some negative pressures that develop just downstream of your spillway gate, right in this area, right along in here. This kind of shows the area, the main area right in here we were concerned with. We were not so much concerned with this area because that was just somewhat of a relic because you were just coming off the spillway gate. But this area in here was indeed creating negative pressures and uplift forces that we were concerned about. The construction of this dam are basically the spillway slabs just lay on the buttresses are held in place by gravity. They're not tied together with reinforcing steel. And so there's a concern with these uplift forces that we could possibly actually lift the slabs off of the dam. Now, the original design basis considered that there was going to be negative pressures on this dam. You're never going to see them in this picture, but right up here at the top of the spillway, there were 3 small vents that were placed in the dam to provide ventilation in this zone of negative pressure. Now, again, the original design storm was considerably lower than the one that is currently at about 1702, 1703, and so these negative pressures were likely lower. But one limitation we had in the CFD model is they were not able to model these point vents in their modeling. It's just something that it's one of those limitations with this, and Dan may be able to speak on that a little bit more. but we were basically showing, let me go back one, we were showing these negative pressures, but we were not able to show if the ventilation that we did have on the dam from original design did anything for us. As you look at this spillway, you can see there's somewhat of an OG shape at the top and bottom, but basically between you're at about a 1 to 2 slope. So it's a very steep spillway. So once we took a step back and looked at it, it's not surprising that we were getting the nape trying to separate from the spillway and creating these negative pressures. So how do we solve that problem? What we decided to do after talking through it a good bit is let's do a physical model. We can physically model what the current condition of the dam is, or the baseline conditions, including the 3 vents that were installed in each bay. We could also confirm the CFD modeling that had been done. We could see if the ventilation we have is adequate, and if it wasn't, we could relatively easily evaluate modifications to the dam to determine how we could possibly address these negative pressure issues. So this is just a profile of the model that was done. I'm sorry about, I can't remember for sure, but I think it was about a 1 to 15 scale. We were having to model bringing air into the flow, and Dan mentioned that sometimes that can be an issue with CFD and even with physical models. So you do have to have a relatively large scale to try to evaluate the air being brought into the flows, the air entrainment. This is just a picture of the model once it had been constructed. Now, physical modeling does have a cost, as Dan had mentioned, but the modifications that were being considered to the dam obviously are considerably more, and we wanted to confirm through the physical modeling if the ventilation we had was doing anything for us, and if it wasn't, finding the best and most cost-effective solution. Through the physical modeling, we were able to confirm the CFD model and that we had negative pressures. What we found was, even in the baseline conditions with the vents that were installed, the 3 small round vents, that it essentially didn't do anything for the negative pressures that were forming. It was probably doing something locally right where the vents were located, but in the overall flow, it was really not reducing them at all. So basically, through the physical modeling, it confirmed that we needed to address the uplift forces that were being created by these negative pressures. It's interesting that we did the CFD model to address an issue with our PMF elevation, and what it helped point out to us is that we possibly had another beyond design basis condition with the negative pressures and uplift forces being created on the dam. I'm not an H&H person. I'm a geotech structural guy, so it didn't jump out at me that we may have a negative pressure issue on a spillway like this. Somebody that does that work a lot more, it may have jumped out at them when they saw the dam. But it was good through this process. We started, for one thing, was helping us find other things that we needed to look at. Obviously, we didn't like that we were finding new problems, but it was good it made us aware of them so we could address them. It basically pointed out that we had either changed or maybe not well understood loading conditions from original design. And just to give you an example of what we're talking about, again, the scale is a little small on this. This right here was the baseline conditions. This is what the existing condition of the dam, as it's constructed. And this is the area of negative pressures. Hold on just a second. Sorry about that. I just lost, I'm coming back in. Okay, there we go. I lost my internet connection. There we go. So this is the area of negative pressure we're talking about, just downstream the crest gates, down into this area. This is one of the modifications we tested. This was the original edge of the spillway. This is the edge of the spillway gate. And one of the things we looked at was just creating a more natural OG shape until we got to the end of the piers. And once we got to the end of the piers, we had separation and flow in this area right here, at which point the flow could ventilate itself and we would reduce those pressures. And what we found is, you can see right here, these were the baseline conditions, and this is the modification we tried just by adding vents. But then these modifications right here is the modified OG shape, and you can see how we essentially eliminated the negative pressure issue. There's still a small amount of negative pressure, but that would not be an issue based on the weight of the slabs, and that could be dealt with by modifying the spillway up in this area. So the physical model gave us the answers we needed, plus allowed us to inexpensively test different modifications to see what would be effective in reducing these pressures and maybe be the cheapest option to fix that problem. One other thing I'd like to mention about the physical and CFD modeling we did on Mathis Dam is that dam had bottom hinge steel gates that had been replaced with Obermeyer gates. The Obermeyers were somewhat curved, more natural shape for the water to spill over the spillway. And we had to confirm that our discharge curve, that we could still pass the same amount of flow we could before the gates were replaced. And since we already had a CFD model in our back pocket, relatively inexpensively, we were able to get Alden to basically check our spillway capacity through the CFD model. And what we found is the Obermeyer gates were actually slightly more efficient because of their more natural OG shape. And so we did not raise our PMF elevation by changing the gates to Obermeyer gates. So we were able to relatively easily confirm that for our regulator. So these issues I talked about, the changes in the HMRs for our PMF back in the 80s, the concern about impacting our spillway bridge because of the changed PMF elevations, all these things I've talked about, where did that come from? How did we know we needed to check those things? Well, we're regulated by FERC, the Federal Energy Regulatory Commission, and Southern Company Georgia Power has a structured dam safety program, and that includes the Part 12D process that's required by FERC, our regulator. The dam safety program that we have dictates that we regularly inspect our dams. This includes internal inspections by dam safety personnel like myself, and also external inspections. We have consultants come in every 10 years to inspect our spillway gate. We do 5-year underwater inspections, and this is all driven partly by our own dam safety program in conjunction with the regulatory requirements for a dam safety program. The Part 12D process comes out of the Code of Federal Regulations, and it's in FERC guidelines if you're not familiar with it. Part of that is what we call the Part 12 inspection process. Paul Sear mentioned he's an independent consultant. That's where he comes into play when he does this he's one of the consultants that does this for us. And basically every 5 years our dams and their design basis are reviewed by this independent consultant. And it's basically to put a fresh set of eyes on our dams and to look at our facilities. They look at the condition of the dam, but they also look at the current stability. They look at the structural design. They look at the design floods that are used. Do you still have adequate spillway capacity? Do you have an adequate surveillance monitoring program? Things of that nature. And I would say, like I said, Southern Company already has a relatively strong dam safety program, but in conjunction with FERC regulator in this process, it really helps us take a look at our dam and realize we may need to evaluate certain design basis standards for our dam. Have they changed since original design and construction? Have they changed because of something upstream or downstream? And I would say if you're not driven by a state or federal regulation to have a similar process, I think it would probably be a good idea for anybody that has a portfolio of dams. Because of the processes that are in place, the Part 12D process and our internal dam safety program, we were able to find these things out and address them, so we didn't have future problems with our dams. So with that, I will turn it back over to Dave.
Thanks a lot, Todd. Appreciate it. So just to summarize for everybody, we had Paul talk to us about how beyond design basis operations can affect dam safety. We had Dan talk about tools for predicting spillway performance, and then Todd talk about the owner's perspective with sort of a case study. And folks can start entering their questions in the chat box on the lower right, but while people are typing in their questions, Dan, I wonder if you want to expand upon some of the discussion that's already taken place through the chat area, and in particular, you know, how when you have validation data for one flow for CFD, how do you know that you're still okay when you go to a much higher flow?
Yeah, so there were a couple of really good questions that were raised, and the first one was that you can kind of points to the fact that you can use a CFD model to extend your physical model results. So I said one limitation of the physical models is that we can't push the flows always to the maximum design flow because we simply can't pump that much water. But if we can validate the CFD model for a series of flows that are less than that, then that would give us confidence in the numeric model, and then we can apply the numeric model for flows that we might not be able to test in the physical model. So that was I don't know if the person made that point explicitly. I think they were, and that's a very, very good point because it's a very valid way that we use numeric models.
But do you want to comment on how you know to trust that? In other words, if you've validated for one flow and then you extend, you're using the CFD model to extend it, how do you know how far you can push it and still be in sort of the envelope of properly validated results?
There's definitely a degree of judgment that goes with that, but if the physics of the problem haven't changed, then we should be fairly confident that if the model got the physics right for the lower flows, it typically does better at the higher flows because the relative grid resolution improves as flow gets higher. It's at very low flows that the cell count, the number of cells that are occupied by the flow field are relatively small, and the more flow that you push, the more cells are occupied by water, and we typically see an improvement in the model performance, not a deterioration.
Okay, great. And next question that came up was, what about modeling for dissolved gas or modeling of dissolved gas?
That's a good question. There are, what we typically do in the modeling of dissolved gases, and I'm going to, this is a specialty of our Redmond office more so than mine, but what we typically do is we put particles into the model and we can see how deep that they go and we can see how long that they are underwater, and then we can use offline models that will tell us for that particular particle depth, pressure, air pocket size, what the change in dissolved gases are. But as far as I know, it is not integral in the current CFD models that it does it automatically and continuously. At Alden, we typically take that calculation offline.
Hey, Dave, I wanted to add a few things just to give some people some perspective. Mathis Dam has 16 spillway bays that are about 16 feet wide. The gates are about 8 feet tall and actually about 7.5 feet tall and impound about 6 feet of water. The PMF discharge for that dam is about 83,000 CFS. Of course, in the physical modeling and in the CFD modeling, because each bay is essentially the same, they were basically they modeled a single bay, then a half bay on each side for the physical model. And Dan, I think this is similar for the CFD. And to do that at the 1 to 15 scale for the physical model, they needed about 12 CFS. So to give you an idea how we were able to model that, again, we were essentially modeling 2 bays, and to match the percentage of PMF passing through those 2 bays, we needed about 12 CFS in the physical model. And then one other point is that we did find in the physical modeling that when we introduced air into the flow to address the negative pressure problem, our PMF elevation did increase by about 0.3 feet. It was at 1702, and it raised it to about 1702.3 in the physical modeling, and that was confirmed in the CFD also.
Great. Thanks, Todd. We got one more question that just came up, which is, why don't regulators demand enough prototype instrumentation to validate design model assumptions? And I think, I don't know, any of the 3 of the speakers might have input on that one.
I'll take a first stab at it, and then hopefully someone else will join in and correct everything that I say incorrectly. One of the challenges with getting prototype data is that you might have to wait for it for quite a while before it actually happens. So you'd have to instrument a large number of dams and then make sure that that instrumentation continues to work while you're waiting for a large flood that you can document. But it's a good question. I don't know. Does anybody else want to address that one?
Again, this is Todd. North Georgia is my project. That's why obviously I seem to know the most about that than some of the other dams we have in our fleet in Georgia. But to give you an idea, again, the PMF at Mathis Dam is about 83,000 CFS, and the highest flow, its flood of record, is about 10,000 CFS. So in 100 years, and we actually have close to 100 years of stream gauge data above that dam. It's not right at the dam, but we have some idea of what passed us based on our spillway capacity and our powerhouse capacity. And the highest flow it's seen in about 100 years is around 10,000. So you know you're just over 10% of your PMF.
Paul, do you have any comments on that one?
Well, I think Todd said it eloquently. I know even with respect to FERC, depending on what you're looking at, especially with the stability, you're often not allowed to extrapolate data that you have maybe for 100-year, 500, even 1,000-year flood. You can't always, they don't let you extrapolate that upwards to the PMF. So, you know, and with state agencies, they're probably less technically advanced than what FERC does. And frankly, trying to do prototype numbers for them, it's not even in the discussions. They kind of dictate, they make their variances. I mean, you can have a high hazard but small dam, and you could go anywhere from a 500-year flood to a full PMF, depending on what state is regulating that.
Right. So Dan, another question for you probably. The question was, can you use CFD to model air entrainment?
In our experience, like I think I said before, for air entrainment as opposed to dissolved gases, sorry about that.
Right.
Yes and no. There are air entrainment modules within Flow3D, and so we can include air, we can include the bulking effects of air. So when you see water coming down a steep chute and it bulks up with air, we can include that, but it requires a coefficient, an air entrainment coefficient that needs to be set, and there's estimates of that, but the question would be, what's your uncertainty on that coefficient, and how does that change the results?
Right, right. Good. Well, I think that's all the questions that we have for today. I want to thank our speakers for the excellent presentations. I want to thank everybody who joined as well. And we will let everybody know when recordings and slide PDFs are available. Thanks very much.
Thanks, Dave.